everyone. Good morning. Thank you all for joining us for our talk on OpenThread today. We are very excited to be here, and we hope this session will be very useful to you all. My name is Vaas Krishnamurthy. I'm an embedded software engineer at Nest.
And I'm Jonathan Hui, principal software engineer leading the OpenThread effort across Nest and Google. In this session, we will introduce to you Thread, a low-power mesh networking protocol for connecting your IoT devices, OpenThread, an open-source implementation of that Thread protocol, and how you, as developers, can start using OpenThread to build connected IoT devices. Now, Thread's history starts at Nest, where our primary focus was to build products and solutions that keep you comfortable while reducing your energy consumption, as well as improving the security and safety of you and your home. Now, in order to achieve that vision, we wanted our products to be able to communicate directly with each other, with cloud services, and directly with the end user via their mobile devices. And so we went looking for a connectivity technology that could satisfy those needs. And in doing so, we set out a number of requirements. The first was that it had to support the Internet Protocol, or IP, because we wanted to build solutions that support a single application layer communicating across multiple link technologies, such as cellular and Wi-Fi. It needed to be scalable because we wanted to build networks that had hundreds of nodes. It needed to be resilient because we wanted to support safety and security applications where devices can communicate even when devices fail or when mains power is lost. It needed to be low power because we wanted battery-powered devices to last for years on very small batteries. And of course, it needed to be secure. But as we went looking for an existing connectivity technology, we actually could not find a single technology that satisfied all of those requirements. And furthermore, as we were talking with others in the industry, we found that many others actually shared the same concern. So in July of 2014, Nest, along with those other companies, started the Thread Group. The Thread Group is a nonprofit organization with more than 100 member companies from around the world. And the Thread Group is responsible for defining and maintaining the Thread protocol specification. It is a market education group promoting the use of Thread in connected products. And it ensures a great user experience through a rigorous and meaningful product certification program. So that was a bit about the history of Thread. Now I'd like to give you some of the technical details of Thread. In short, Thread is an open, IP-based, secure mesh networking protocol for IoT devices. Now, while Thread is a new link technology, its design utilizes existing technologies wherever possible. At the radio layer, it uses IEEE 802.15.4. It's the same radio that Zigbee uses and has been using for the past 15 years. And using an existing widely deployed radio technology allows Thread products to achieve a fast time to market, as well as leverage existing economies of scale to deliver low-cost solutions. At the network layer, Thread uses existing IETF standards for transporting the Internet Protocol version 6, or IPv6, over 802.15.4 radios, a technology called 6LoWPAN. Now, Thread's support for IP is a key differentiator. Most existing low-power technologies do not support IP. And so why is IP so powerful? Well, for Nest, it means that we could build solutions that utilize number link technologies, such as Wi-Fi, cellular, and Thread, and have all those devices communicating securely end-to-end with a single application layer, and not have to build application protocol translators in between. And at the same time, it means that we could have a single network supporting multiple applications simultaneously. IP makes it easy to deploy new applications because you don't have to worry about application protocol translators in the middle. And that was a key reason for the success of the internet and its rapid growth. And Thread extends that benefit to low-power IoT devices. So Thread operates as a scalable mesh. Thread supports up to 32 routers that are responsible for forwarding packets throughout the network. At the same time, each router is capable of attaching 511 end devices. As a result, Thread can easily scale up to hundreds of nodes in a single network. Now, Thread self-selects the set of routers and scales gracefully to different network needs. All devices initially attach as an end device, but when additional connectivity is needed, a Thread device may elect itself to promote itself to become a router. However, when a router does determine that its connectivity is redundant or unnecessary, a Thread router can demote itself back to an end device. So Thread is resilient. Thread routers perform a dynamic, shortest path, any-to-any routing protocol. If you're familiar with routing protocols, it is in the class of proactive distance vector routing, similar to RIP. In short, it means that each router maintains and advertises the best next hop towards every other router in the Thread network. This dynamic routing protocol not only allows Thread devices to efficiently forward packets throughout the network, but it also allows Thread to dynamically react to node failures and radio connectivity loss. Now, Thread's resilience extends beyond the mesh when communicating with devices that are outside Thread network. Thread supports multiple border routers operating simultaneously, providing multiple paths into and out of the network. Most other technologies rely on a single hub or coordinator for external connectivity that represents a single point of failure, and that's largely because those protocols require a stateful application in between, a stateful application gateway in between to connect that network to other networks. But with Thread, you truly have no single point of failure, whether that means you're communicating with other devices on the mesh network or devices off of the mesh network. So Thread is low power. Compared to Wi-Fi, the 802.15.4 radio itself consumes about 1/10 of the power in active receive mode. And when you combine that with the fact that Thread can sleep end devices the vast majority of time, it means that Thread devices can operate for years on very small batteries. And Thread is also secure. Thread protects all data traffic at the link layer using AES 128 encryption and authentication with replay protection. And unlike other existing technologies, security is mandatory in Thread. There is no way or option for you to deploy a Thread network with security disabled. And what that also means is Thread had to solve the secure device commissioning problem in a very user-friendly way. Via mobile device, they open a mobile app and discover Thread border routers on their network using MDNS. They then establish a secure connection with that border router, and then go over and, with their mobile device and scan a QR code of the device that they want to join and obtain a short pairing code. The mobile device then establishes a secure DTLS session to authenticate the joining device and securely provide the credentials. In fact, if you've used a Nest product today, you'll find this process is very similar to what you've experienced. It really is very simple and intuitive for the user, and you'll get to see a demo of that in a bit later in this session. So in summary, Thread supports all of the design requirements that we set out in the beginning. It supports IP for secure end-to-end communication without application gateways. It supports hundreds of devices in a single network. It has no single point of failure. Supports lifetime in years when operating on batteries. And has mandatory security with a very user-friendly commissioning process. We started that effort in 2014. 4 years later, we believe Thread is still the only communication protocol that satisfies all of those requirements. Now, 2 years ago, here at I/O, we launched the OpenThread project. OpenThread is an open source implementation of Thread, and it is the same implementation that we use in Nest products today. And the goal of OpenThread was really to make the same technology that we use in Nest products more broadly available to developers, and that means you. So OpenThread is an open, community-based project, and it's hosted on GitHub. All development is done in the open. Every commit goes through a public pull request where anyone can comment on and review. And anybody can make their own contributions by submitting issues or pull requests themselves. OpenThread is also licensed under BSD3. And since its launch 2 years ago, OpenThread has seen widespread adoption. OpenThread has been ported to about 10 different 802.15.4 radios, and you can find example drivers for those radios on GitHub. Furthermore, many of the silicon providers provide direct commercial support of OpenThread running on their silicon and in their SDK. So if you're already working with a favorite silicon vendor of yours, I encourage you to reach out to them regarding support for OpenThread. And OpenThread is also seeing strong adoption by IoT platforms. Of course, Android Things, but also Particle, Runtime, and Zephyr. Now, in addition to the core Thread implementation, there are a few other sub-projects that I do want to mention. The first is WPAN Tundi, a user space network interface driver for Linux. And remember that Thread supports the same IP technology that drives every internet-connected device. And with WPAN Tundi, you can present a Thread network as a standard network interface in Linux, which means you can use the same socket APIs that you're used to using to communicate with Thread devices. OpenThread also has a border router subproject, and it builds on WPAN Tundi to provide a quick and easy method for you to connect your OpenThread devices to Ethernet or Wi-Fi networks. And you can do that using Raspberry Pi or BeagleBone Black. And all of the source code is available on GitHub. So as I mentioned, OpenThread is shipping in Nest products today. And what that means for you is that you also get to take advantage of all of the hard work that we put into making OpenThread work really well in end consumer products. So let me tell you a little bit about how OpenThread really enables Nest products. The Nest Detect is a wireless open-close sensor for things like windows and doors. It's also a motion sensor. And it communicates only via Thread and does so as a sleepy end voice, allowing its radio and processor to sleep more than 99% of the time. But when it does detect an event, such as opening a door, it can quickly wake up, communicate that event, and set off the alarm. And by using Thread, Nest Detect is able to operate for 2 years on a small CR123 battery. The Nest DL Lock is a connected deadbolt for your door. Like Nest Detect, it relies only on Thread to communicate and operates as a sleepy end device. And by using Thread, not only does it last for years on AA batteries, but it can also respond to remote lock-unlock commands within seconds. So it's very responsive. And remote unlock is an excellent example of where you want secure end-to-end communications, and Thread supports that by supporting IP. Now, the Nest Guard is a Thread border router that connects both the Nest Detect and Nest DL Lock. It is a Linux-based Thread border router supporting Wi-Fi and cellular in addition to Thread. It uses WPAN Tundi to expose Thread as a standard network interface to Linux-based services and applications. And it has a 12-hour battery backup with cellular to ensure that your Thread network stays connected and can communicate alarms outside your home even when power is lost or Wi-Fi goes down. And then we have the Nest Connect. It also serves as a Thread border router, connecting the Nest Detect and Nest DL Lock. Like the Nest Guard, it is a battery-backed border router, allowing it to maintain Thread connectivity even when power is lost or even when Wi-Fi is down. However, unlike the Nest Guard, Nest Connect is an RTOS class device and only supports Wi-Fi and Thread, allowing us to really drive the cost of that device down. And with that, I'll turn it over to Vaas.
Thank you, Jonathan. I've been at Nest for over 5 years, and I've enabled the 15.4 radio on several Nest products. So for the rest of the session, we're going to talk about how to take OpenThread and other open source resources available to quickly build your IoT device. With OpenThread being highly portable, platform agnostic, and IPv6 based, this opens up a large number of options for us. So we have several system architectures, operating systems, tool chains, and radios to pick from. So we're going to talk about each of these categories and figure out how to make the right decisions for your product and what the deciding factors are. So let's start with the system architecture. We have 3 models to pick from. The first one is called System on Chip, or the SoC model. Here, we only have one processor, and both the application and OpenThread run on the single chip. This model is typically picked for a device that has a simple function, and more importantly, for a device that runs on battery power. An example of this device is the Nest Detect, which is the motion sensor for doors and windows. And the role of this device on the Thread network is a sleepy end device, and it needs another fully powered Thread router to act as its parent. There were a lot of features added to OpenThread and parameters provided to get this device to run on a single battery for over 2 years. So all of that is available in OpenThread for everyone to use as well. Most radios typically come with the single thread chip, but some today also have an integrated thread and BLE radio. So we have the option to use more than one interface for communication. The next model is called the NCP, or the Network Coprocessor Architecture. Here, the radio is its own chip, and we have a separate host processor. Now, this gives us a lot more flexibility. We can choose a host processor that's a lot more capable, and we get the processing power to run more complex applications. We can even have a nice UI, like a display, touchscreen display, voice assistant. You can have a Wi-Fi radio to connect to the cloud, and so on. An example of this device is the Nest Guard, which is the security hub. It has a keypad, it has a speaker, it has several radios, sensors, it has the Wi-Fi, BLE, cellular radios in addition to the Thread radio. The role of this device is a Thread router, and it's meant to operate as an always-on, fully powered device. But with this NCP model, we also have the option of having the host and the radio sleep independently. So when it's always on, both the host and the radio are awake. But when this device loses external power, it can run on battery backup for up to 12 hours. So at this time, the host sends this information up to the cloud, and it immediately goes to sleep. The radio, however, continues to act as a thread router and can wake up the host whenever needed. Another example of this model is the more power-constrained Nest Protect. This is our smoke detector. It's battery-powered. And in this case, both the host and the radio are always asleep. And again, whenever an event happens, one can always wake up the other. The next model we have is the Mac and Phi architecture, where again we have two different processors for the host and the radio. But in this case, the OpenThread core runs on the host processor instead of on the radio. And this model is great for adding 15.4 thread support to existing products. You can simply attach a 15.4 radio to an existing device and add thread support to it. Since this model is simple to use and it has a quick system integration, it provides the fastest time to market, and it also offers the lowest 15.4 component cost. So depending on your application and your product, what your power constraints are, what your UI looks like, what are the radios you have, you can pick from one of these three different architectures. Next, we pick the operating system. OpenThread is platform agnostic. So when we choose the operating system, we simply base it on the complexity of your product. So for something really simple, like actuator or a sensor, we can go with the bare metal operating system. For something a little more complex, we can go with the free RTOS. And for much more complex applications, we can go with Linux or a Linux-based operating system like Android Things. The Nest Detect uses free RTOS for its operating system and LWIP for its networking stack. The Nest Guard uses Linux for its operating system on the host, and FreeRTOS for the operating system that runs in the radio. So all these operating systems, networking stacks, and OpenThread are all open source. So we can quickly start adding your application support on top of this layer. OpenThread is also toolchain agnostic. So it not only runs on these several operating systems, but you can also compile it using several well-known toolchains. So we pick that basically based on whatever you're most comfortable with. OpenThread also provides a narrow platform abstraction layer. So all of these are great for us to achieve very quick system integration. Next, we pick the radio. There are several radios available today that can run OpenThread, and we are not limited to this set. It's easy to port OpenThread to a new radio if you want to use it. Each radio here has a different power, memory, and cost associated with it. And depending on the exact features and memory, each of these range anywhere from 80 cents to $2. So to determine these requirements, it's best to think of the network as a whole. So how many routers do you have on the network? How many sleepy end devices do you have? How many sleepy end devices need to be supported on each router? So what is the expected battery life of your sleepy end device? There is always a trade-off between how often the sleepy end device polls versus its battery life. If you have to poll too often, then it's going to drain the battery quicker. So first, we determine this data poll rate. And that, on the other side, for the router, determines how long each packet needs to be queued for the sleepy end device. And the application itself will determine how large these packets are and how many such packets need to be queued for the sleepy end device. Now, multiply this by the number of sleepy end devices this router needs to support. So that gives us the minimum RAM requirement for this router. So once we nail down the network and memory requirements, we can pick from one of these radios. So at this point, we can get a couple of these development boards because we made decisions on the operating system, tool chain, radio, and system architecture. And we can try out our sample app. So OpenThread provides a very simple-to-use command line interface. So we can do a lot of things to exercise various features of Thread. You can form a network, scan, join, look at your neighbor table entries, look at your child table, look at the signal strength with each neighbor that you have. You can ping one device to another in the network, and so on. And for a host and NCP-based platform, you can do the same thing with our WPAN-Tundi tool. There are also several code labs you can try out. The code labs can either be run on 2 physical devices, these development boards, or you can run it simply with OpenThread in simulation mode. So at this point, we can start building your IoT product by adding application support. Now, let's say you're building an app that has a light bulb controlled by a remote switch. You can start building this by writing device drivers for your product. The radio drivers themselves are provided by the radio and platform vendors, so that's something we don't have to worry about. And if your network only has device-to-device communication, we are good at this point. However, if you want to send the light's state updated to a web app or your mobile phone, we have to add additional border router and cloud support. And for the application itself, we can write our own, or we can leverage one of several applications that were written specifically for connected devices. Since Thread is IPv6 based, we are not limited to this. There are a large number of options to choose from. So this gives us everything from application layer security, connection, communication APIs, software download APIs, and so on. So we can take advantage of this layer and hook up our application on top of this. So the next piece to the puzzle is addressing. So how does your switch know the address of the light it's communicating to? How does your light know the address of the cloud service that it needs to send updates to? Thread supports standard IPv6 mechanisms for local and wide area connectivity. So all we are really doing is building a normal IP network. So everything from assigning, discovering, to addressing is exactly what we do for a traditional IP network. For Nest products, we have picked a certain naming and addressing schemes, a cloud connectivity model, and application layer security. This layer is what we call Weave. And we've recently open sourced it. It's called OpenWeave. We also have a code lab set up here at I/O that everyone can try out to understand what Weave is, what it can do, and how to use it. So now that we've essentially built our IoT device by adding application and addressing support, our next task is to make the network strong and reliable. And OpenThread provides a number of features and parameters that help us with this. First, OpenThread is extremely configurable. There is pretty much everything that you want. You can change from timeouts to number of children that you want to support, how large the buffer is, and so on. You can turn on and off features very easily by putting in some defines in a configuration file to make the stack do exactly what you want. OpenThread also has configurable logging, and this logging is configurable runtime, and that's the most important thing. So say you are debugging a network issue, and the network is working great for several days, and occasionally there is an error. It doesn't make sense to have verbose logging that entire time. So what we could do is at runtime, when that error happens, you can turn on extra logging just during that error condition. OpenThread also has a great set of counters. We can see everything from the number of packets transmitted, received, dropped in every layer, from PHY to MAC to IP layers. We can look at the transmit error rate tracking and so on. So all of this helps us with getting a deep insight in the stack, and we can debug really easily with this. OpenThread can run in simulation, so we can emulate an OpenThread device using a POSIX process. So if you want to test a certain scenario over a large number of devices, we can do so using the OpenThread simulator. Next, we have Torrent. This is a Python-based testing framework developed by our colleague Aptin. It's very simple to use, and you can see an example of it right here. So you can create a number of nodes, and what you can do is you can tell the script that I want to have only these devices join me, and I want to have these devices blocked from joining me. So with this, we are able to create complex network topologies. So you can run a certain scenario over multiple hops, or you can force a packet to take a certain route through the network. Next, we have a thread topology monitor. This is something our team in Shanghai put together for I/O. It's actually live and running in our sandbox. And this is basically a live interactive network map. It gives you the device roles. It tells you what type of devices are used, what radios are used, and so on. And this will soon be open sourced as well. OpenThread supports standard Wireshark traffic captures. So we can get one of these dev boards, just load the standard NCP image. It's a pre-built NCP image, and that's it. We can start sniffing immediately. So the other cool feature is that the radio can simply be in monitor mode, where it's just passive and acting as an external sniffer, or a device that's part of the network can be put in a promiscuous mode, where it's a part of the network and still capturing packets. And this is, again, a great debugging tool. So if you're looking for a lost packet, you can pretty much have the sniffer running on all devices while it's on the network and look at their PCAPs later to determine where the packet was dropped. So as you can see, all of these tools were developed for OpenThread to make it really easy to debug. And as a result, we are able to create a really stable network and higher quality products. So at Nest, when we started using OpenThread in our products and testing it more in real-world conditions, we discovered several use cases, and we started adding features around each one of them. So OpenThread is not only Thread 1.1 compliant, but it has a lot of features that in some cases are crucial for the success of shipping products. There are several such features, and I've listed a bunch of my favorites here. So there is channel monitor and channel manager. So Thread operates on 2.4 gigahertz, the same frequency as Wi-Fi. So to avoid interference, we monitor all Thread channels, we collect data over days, and we move to a clean channel from time to time. So that's the channel monitor and channel manager. There's another important feature, jamming detection. So we are able to detect when our network is being jammed, and we can alert the application. Another interesting feature is the periodic parent search. So when we first started working on our Nest Guard and our Nest Detect, we made the network really, really strong between them. So we tweaked a bunch of parameters and made the connection so strong that when we deployed them and we introduced a new router in the middle, like the Nest Connect, the problem was this device is sleepy, and it was trying so hard to maintain the connection with this existing parent that it could not move to this better parent, this potentially better parent. So we introduced this feature called periodic parent search, where every so often the device will look for a better parent and move. However, we couldn't do this too often, because every time we were doing this, we were keeping the receiver on for 8 seconds, and that eats into the battery life. So we did some computations and came up with 10 hours as our number. So every 10 hours, our Nest Detect will look for a better parent, and even if the network topology changes, it will form the right parent. And now we ran into another use case. So this device in the middle, this new parent, say, gets a software update. It reboots, and at this time, the Nest Detect immediately goes back to the less appealing parent. And now it doesn't make sense for us to wait a whole 10 hours. So we detect an involuntary detach, and we check again in 10 minutes to go back to our better parent. So a lot of such features were added, and all of these are practical use cases that every product out there will run into. And Nest has already gone through the process, and we've added several features that help everyone. So in addition to those, there were also really small but high-impact improvements that we've added. So we talked about this parent switch, right? So each parent remembers the information about a child until a certain timeout. So what happens is, when this child moves to a different parent, the old parent does not know that it's gone. So it continues to queue packets for this child. So we added another feature to tell the old parent that the child has moved on, requesting it to remove it from its child table. So a lot of other changes were added as well to get a better sleep current, and so on. So to sum up, there are a lot of useful tools and a great number of features that were added to OpenThread on top of Thread 1.1. And I also want to point out that OpenThread was not designed just with Nest products in mind. Our goal is to accelerate the development of connected devices everywhere. So we not only made it open source, but we've also added several features that Nest doesn't even use, like DHCP, DNS, and CoAP. And these are very useful for existing internet-based devices to adopt Thread. So please make use of these tried and tested platforms and the open source platforms and tools, and let's bring more of those connected devices online. So with that, let's check out some demos. What we have here is several development boards all running OpenThread. So we have an Android Things board here. This is the IMX70 PicoPi board. This is acting as a host. It has an LCD screen, and it has a speaker attached to it. There is also the Scilab's Thunderbird. This is acting as the NCP for the Android Things. We have a couple of Nordic development boards here acting as a system on chip, one as a switch and the other one as a light. We have a couple of Raspberry Pis here set up as border routers, each of them using a different radio. One is using the TI radio, another one is using a Nordic dongle. We have a Scilab's Mighty Gecko EFR32 development board. And I also have an NXP dev board here that I'm going to use as my sniffer. So before we get into the actual demo itself, I want to show you some tools and resources and how to get to each of these platforms. So I'm going to plug in this sniffer into my laptop. And first, let's go to our GitHub page. So this github.com/OpenThread, this is where we go. So we have the code for OpenThread, border router, WPAN Tundi, and PySpinel. The PySpinel is the tool I'm going to use to start my sniffer capture. Hold on one second. I think maybe this is it. OK. All right. I may have to open a different serial port here. And OK, I think that looks a bit better, maybe. Anyway, so while that's going in the background, so that's the sniffer that's running the standard NCP image, starting to capture packets that are flowing between these two devices. So I have a Nest guard and a Nest detect here. So you can see there are data requests and IP packets flowing back and forth. And this is just standard Wireshark that you see here. So I'm going to log into this device and show you some things there. So I'm logged into the device. And I'm going to use a WPAN CTL, which is the tool used by WPAN Tundi. It's a command line interface. So we can do WPAN CTL status to look at the status of the network. We can do a WPAN CTL get. And this prints all the parameters that we have associated with this network. And these are the counters that I was talking about. There are so many useful counters to track various things. These are great debugging tools. And let's so what I'm doing here is just showing you the logs. Apparently, I don't see any logs. I have a typo there. Sorry. There. So here, this is what the logs look like, and they're really great. So you can see these are just standard IP packets. You can see these IP packets. We can see data poles received from this device to this device, and so on. And I can also send a ping from one device to another. And that's just a standard IP ping. And if I go back to my Wireshark, there it is. So if you're familiar with this tool, you'll immediately recognize that these are just standard IP pings and standard IP packets. The next thing I'm going to show you is OpenThread.io. this is the page that we recommend going to. And here, you have all the information that you need here. So you go to Platforms, and here is all the development boards that I have over there. And you can click on any of them, and that will take you to their GitHub page, where they tell you how to build the samples, how to load the code, and run the example. And if we go back, we can see other operating systems. We see the Linux-based operating system. We have Android things, NCP platforms, and the border router support. So there is the Raspberry Pi border router support, and I've used this exact example to replicate the setup over there. So I'm going to show you how that works. So that border router is advertising an AP. OK, so here. So first, we can open up a web app. I'm connected to that AP, and I'm directly typing in the IP address of the device. And now I can directly start controlling the network from this web GUI. So I can say, for example, I can form the network from here. So it's going, and I can open up the thread commissioning app. So this can be downloaded from Google Play. And this will detect the border router first. Let's see if it's connected. There, it found the border router. Now, to add a device to the network, I'm simply going to scan its QR code. And when I do that, the QR code contains information about the serial ID of the device and its pairing code. And there, the thread device got added to the network. And I can do the same thing using this sample I programmed in the Android Things board. And there's a speaker attached, so you might be able to hear what it's doing as I'm typing. So I can look at the network info, current network info.
The device is offline.
It says device is offline. I can scan.
Scanning for networks.
I find my network, and I'm going to connect to it.
Joining OpenThread demo.
And
the device is attached.
So there was a simple app that is also available on GitHub that you can try out. So now I'm going to show you the OpenWeave demo. So this is similar to the one that you have in the code labs. This is just a result of the code lab, and we're going to go over that. Now, what we have here is a device configured as a switch and another device configured as a light. And this pretty much is just turning on the light, and there's a lot of mechanics that go into it. So the light turned on, and the light turns off. So what this is doing is sending a weave packet, which is encapsulated in an IP message, going over the thread radio. And the other thing that also happens at this time is we have a cloud service running over there, and every time I change the state of the light, that gets updated in the cloud. And that happens because this information goes via thread to our border router, and the border router is connected to our Wi-Fi AP, and it uploads it to the cloud. So that concludes our demos. Thank you. Thank you. We'd love to hear from you. Please provide us some feedback at our I/O schedule page.
Yes. So that's all we have for you today. Thank you very much for coming. We really hope you enjoyed this session. I encourage you to go over to our IoT sandbox, which is just next door. You can see more demos, see more things happening, meet the rest of the team. And after tomorrow, you can check out more information at openthread.io, github.com/openthread, and go to Google Groups OpenThread-users. Thank you again for joining us. Have a great rest of Google I/O.